Hey everybody. So in this video we're going to talk about functions. The idea of a function is so central to all of mathematics that you absolutely have to be rock solid with the fundamentals to be able to do anything useful in mathematics. So let's talk about that a bit. And let's start with the fact that unfortunately what a lot of students study as they learn math is they usually take what is labeled as a pre-calculus course. And presumably that's meant to get them ready for a calculus course. But what is pre-calculus? It's an introduction to the idea of function and sort of an extended tour of the various common types of functions. So in other words, it's a trip to the zoo. You learn all about these different kinds of functions and the kinds of behaviors they have. What do you do in calculus? What you really do in calculus is use advanced methods. And these methods come from using limits and using those limits to find things called tangent slopes, and you can find areas under curves. There are all sorts of things you can do in calculus, but all of those things you do have to do with analyzing functions. So really you can encapsulate the whole of calculus by saying it's just advanced methods for analyzing functions. So what's going on here? Both of these classes have to do with functions. So if I had my way, I'd probably not call this first course pre-calculus. I might call it the fundamental analysis of functions. And calculus should be the advanced analysis of functions. But in either case, you're analyzing functions. So please don't lose sight of the fact that what you really need to understand, no matter which course you're dealing with, is what is a function? What are the parts of a function? How does a function behave? What is this particular function doing? So it'll help you a lot just to keep that sort of frame of reference in mind. So let's talk about what a function is. A function from the set A to the set B is a rule that unambiguously assigns to each element of A some element of B. Now this sounds very abstract. And so what do we mean by a rule? That's kind of an ambiguous word, perhaps. So a rule could amount to a set of instructions, a formula, or simply a declaration. So this rule may or may not have a common sense interpretation. It can be very abstract, for instance. And the only requirement is that one must be able to determine unambiguously what the assignment is. So, I mean, if you've successfully defined a function, you may not even know what it has to do with anything, but you should be able to find the rule that tells you how to assign elements of B to elements of A. All right. So let's get a little more specific. Let's look at an example. So suppose your set A was a collection of characters. So you've opened up some sort of video game. You've got these characters. And then your set B is a set of weapons that they're supposed to select before they go on their journey in the game. And so once you make that selection, say, then what you have defined is exactly a function. It's an unambiguous assigning of a weapon, in this case, an element of the set on the right-hand side, to each element of the set on the left-hand side, a character. So having chosen one unique weapon for each character, that's a function, okay? So if you've ever played cards, you're probably aware of this function. Not that you've ever taken the trouble to sort of think about it explicitly, but suppose A is the set of suits. So there's hearts, spades, diamonds, and clubs. B is a set of colors. Let's just suppose it's the set of these four colors, red, blue, black, and green. So there is, of course, a function which simply assigns to each suit what color it's supposed to be. And so that is a perfectly reasonable function. And if you looked at sort of a Venn diagram, like we had a moment ago, you would see something that looks like this. We could give this function a name, f. So we could say f is this color choice function that assigns to each suit, i.e. element of the set A, some color, i.e. element of the set B. Now a couple things to notice. Both black and red get pointed at more than once. That's okay. A function can deal with that, okay? The idea is you just have to find an unambiguous rule for each suit, and it certainly is unambiguous. You don't look at the diamond on the left-hand side and say, well, let's see. The arrow, if you had an arrow that pointed to both red and blue, that would be trouble. That's ambiguity. You can't say, well, I have a choice. You don't have a choice. A function tells you where to go. So the fact that black and red get pointed at more than once, no problem. That's okay. There's also something else that's okay. Green and blue don't get pointed at all. And that's okay too. You don't have to, the set of things that you're pointing to, you don't have to hit them all. That's fine. It's just the rule is everything that you plug into the function, right, the things you assign things to, that has to be an unambiguous rule. That's the only real stipulation for a function. Now, some of you may have seen something like this before. You can think of a function as being sort of a Dr. Seuss-like machine. And what it does is it takes inputs, and you feed it inputs, and then somehow something happens, and you get an output, okay? So the things that you're plugging into the top are the elements of the set A in our definition, and the things that are coming out have to be from the set B. So let's get some technical language on the board here. Usually we're going to refer to the inputs, the things you plug into a function. We're going to call those arguments. Okay, so an argument is something you plug into the function, and the output, the thing that comes out, is, we're going to call that a value. Now, I realize value is a word that gets used a lot in math in different contexts, but usually in the context of discussing functions, I hope it becomes clear, unambiguous, that value, I mean, is the kind of thing that comes out of a function. Okay. So there's this thing called function notation. When we have something like this, usually the way we write this relationship is f of an argument equals a value. Now, the thing at the top and the thing at the bottom look very different, but they have exactly the same sort of semantic purpose. They do exactly the same thing. It's just the top is a little more fun. But when you look at function notation, that's really what's going on. You're seeing that as the argument, the thing you're plugging into the function, and then you see the value, the thing that comes out of the function. And this is also something to keep in mind as you move forward. So in our deck of cards function, our suit color function, our function notation would look like this. F of clubs is black, F of spades is black, F of diamonds is red, and F of hearts is red. Okay, so function notation, you may not be used to it, but you can use it in very abstract settings. You don't have to have numbers. Here's a function I grew up with, some tasty cereal that I think it got fancier over the years, but basically it had all these marshmallow shapes in it and had different colors. Actually, you can see a modern picture now. They've now got multicolor marshmallow bits, so I don't think my function's even up to date. So maybe this isn't a good example of a function anymore. But what kinds of functions will we be dealing with? Well, almost invariably what we're dealing with are functions where the input is a real number and the output is a real number. Or I should say, the argument is a real number and the value is a real number. So let's draw a Venn diagram of a function that goes from R to R. We'll look at the squaring function, the function where you take the argument and you square it to get your value. Now, you could just start looking at a whole bunch of numbers and just seeing where the arrows go, right? 1 squared is 1, negative 1 squared is 1, and so on. You could draw a whole bunch of arrows. This seems like a pretty pathetic way to try to encode what the squaring function is doing. I mean, it's just a mess. This kind of diagram makes perfect sense for the suit color function and the character weapon function we saw at the beginning of this little video. But for this function, I think we're missing the point. The real numbers all align themselves on these nice lines. So we could at least, instead of the Venn diagram, we could at least look at the real number line in each instance, and we could look at these arrows that point to what happens to each of the arguments. Okay, so we got arguments on the left and values on the right. But even this is not so helpful. It's a little more organized, but still we're sort of missing the point here, because what we could do is we could take these real axes and just turn them 90 degrees. And what we're going to do is we're going to think of this horizontal axis as being the argument axis. And the vertical axis we're going to think of as being the value axis. Okay, so now when we look at the squaring function, and for example, negative 1 is the argument and 1 is the value, negative 1 squared is 1, what we'll do is we'll look along the argument axis for negative 1, we'll look along the value axis for 1, and we will plot the point negative 1, 1. So you'll notice what happens here is, this is very much like the arrow diagram we had a moment ago, but instead of an arrow, we just use a point. Okay, so negative 1 is our input, 1 is our output. 0 squared is 0, so we'll look for 0 on the argument axis and 0 on the value axis, and we'll plot 0, 0. 7/4 is the argument. We square that, we get 49/16 for the value. So we'll look for 7/4 on the argument axis and 49/16 on the value axis. Argument, comma, value, there's our point. And so you just wind up plotting a bunch of points. course, that's going to be tedious, so you can get some help with, well, you can either look for a pattern or you can use some software, but in any case, what we'll get in this case is a nice parabola. We know that the squaring function has a nice parabola as a graph, and so now this representation of a function looks beautiful. All of a sudden, we're starting to see, potentially, if we know to look for it, all sorts of patterns, statements we can say. For example, if this is what our graph looks like, we can notice that the value is never negative. We don't see any part of this graph lying below the horizontal or argument axis. In other words, the values are never negative. So we knew that because when you square a real number, you get something that's either 0 or greater. So we didn't learn anything new, but you can see that relationship encoded in this graph. Okay, so there's all sorts of information you can glean from a graph. Okay, so this is the graph of a function f. Let's call the squaring function f. Let's give it a name. We'll call it f. And what we'd like to do is set up a formula for f. It's not that challenging, but I want to point out some notational issues. F is the name of the function. All by itself, sitting there alone as a letter, that is a name. So, you know, Bob is a name. Well, what can you say about Bob? Bob is in 10th grade. Bob lives in Vermont. You could start listing characteristics, but by itself, you just have a name. That's what's happening here. We're going to give the name of the function. We're going to call the function f. And if we do that, then if we just invoke this single symbol, we're talking about the function. It has many different properties. But if we want to say what it does to an argument, we would use this notation. We say f of x. So now we're looking at not the name of a function, we're looking at a value. We're getting an output when we look at this notation because now we've plugged in an argument x into our function. So f of x is a value. It stands for a number in this case. Let me back up for a second. This by itself represents a function. It's a complicated gadget. This notation represents a number. It's the value of the function when you plug in the argument x. It's important to keep that distinction in mind. But let's move on. We want to find a formula for this. So what we're going to do is we're going to say this is defined to equal. You may not have seen this symbol before. What does this symbol mean? This symbol indicates that what you're about to be shown is how to find the values of the function f. We are defining what it means to take f of x. Another way to look at this is when you see this symbol, a colon followed by an equal sign, it means equal by definition. They're not accidentally equal. They're not we're not setting them equal and then we're going to find a solution. We're using a special symbol here that means here's what I'm saying when I write the thing on the left. So the left thing, how do I find the value of the function f at the argument x? Well, I need to square x. Okay? So when you see this notation, that's what it means. It says I'm defining a function f, and here's how I'm defining its values. Here's how I calculate its values. This is what f does. F takes x and it squares it. Okay? So there's some notation there. So there's our function. And this, we call it the graph of the function f. And again, something to keep in mind, a function and its graph, different gadgets. The graph is a graphical representation of what f, the function, does. It's not the same. So when you really should be careful about talking about the graph of f as opposed to the function f, or even the value of the function at an argument, f of x. F's the function, f of x is the value at the argument x, and then we're looking at the graph of the function f. So sort of three related, obviously, but different gadgets. So the graphical representation of a function, so you might call this the golden rule of precalculus. If you ever look at the graph of a function f, then if you notice that the point a comma b is on the graph of f, well, the point AB is on the graph of f if and only if f of a equals b. You might think this is obvious, but I can't tell you the number of times where just remembering this fact is very, very helpful to moving forward in a problem, not just in precalculus, but in calculus and beyond. So you really want to remember this sort of golden rule of precalculus. Domain and range. So a couple definitions. The domain of a function is the collection of all its arguments, and the range of a function is the collection of all its values. So if you want to go back to this Dr. Seuss-like picture, the domain is just the set of all the numbers you can plug into the function, and the range is a set of all the numbers that come out of the function. By the way, I shouldn't have said numbers because this definition works in the more abstract setting as well, with the sort of suit color function and the character weapon function we saw before. So it doesn't have to be numbers, just sets. So the domain is the set of all numbers you plug into the function. The range is a set of all numbers that come out of the function. And so how do you read domain and range from a graph? So suppose you have a graphical representation of your function, and you're asking the question, what's the domain? So you could just ask yourself, of all the points that are on the graph, let's figure out all the arguments I can plug in. Well, graphically, what that means is find all the x coordinates of points on the graph. So we're going to sort of single out these first coordinates here. And so you can imagine that the graph is a bunch of points on the graph, and you just smash them all to the x-axis, and you can easily visualize what the domain should be. So this is going to be the interval from A to B, open on the left, because that little open circle means you don't quite include the argument A, closed on the right, so it's this interval here is our domain. Now, how do you read off the range? So in this case, what we're looking for is all the outputs, in other words, the y coordinates. So again, we're going to imagine the graph as a collection of points, and this time we're going to smash all of our points and sort of project them onto the value axis. And in this case, we get a closed interval from P to Q. So the range in this case is the closed interval from P to Q. Now, let's end this with 7, in fact. I'm going to ask you 7 questions, and you can pause the video if you want to try to answer it before I just give you the answer. I'm not going to give you any graphical clues as to the solution. I'm just going to read off the solutions to you, and then add some commentary. But question, what is f of -2? Well, f of -2 is 3. Question number 2, what is the solution of the equation f of x equals 2? So my first bit of commentary here is you can see why the colon equals notation earlier was important, because now you could look at that and you can say, wait, are you redefining a function? Is my function now the rule that tells me that all the values are 2? No, I'm now talking about an equation. I'm saying f is a function and you can find its values, but I want to know when the value of the function is equal to 2. So in this case, what we're looking at is a solution that we need to, an equation that we need to solve. This isn't somehow a redefinition of our function f. I've got the function f graphed and I'm trying to solve this equation. So what is the equation of, what is the solution of this equation? Well, it turns out there are 3 solutions. If you drew a horizontal line at y equals 2, you'd see that the graph intersects 3 times. That means there are 3 arguments you can plug in to get the value 2. And if we assemble them in set notation, then the set of solutions is simply -4, -1, and 3. Next question, is 4 in the domain of f? And the answer is no. You can see from the graph that if you plug 4 into the argument, you find 4 on the argument axis, you look high and low along the other direction, the vertical direction for a value, you don't have it. 4 is not in the domain. So what is the domain of f? Well, the domain is the closed interval from -4 to 3. What's the range of f? The range is the closed interval from -2 to 3. What is the maximum value of f? Well, the maximum value of f is 3. That is the largest value you can possibly get out of this function. So that's what we would say in this case. The maximum value of f is 3. What argument minimizes the value of f? The argument that minimizes the value of f is 1. Now, if you got that question wrong, I suspect strongly that what you did was you answered a related but different question. You may have answered the question, what is the minimum value? If I had asked that question, the answer would be -2. That's the minimum value, but that's not, -2 is not the argument you would use to get that minimum value. 1 is the argument you would use to make sure you get as small a value as possible. So read your question carefully, right? The argument that minimizes the value of f is 1.